All right, so I wanted to take a little bit of time. So rather than kind of shoehorning module 2 into today, I thought it would make sense to take a little bit more time and talk about some different kinds of unit conversions that exist. Because ultimately, these ones that we're talking about are the ones that are the more difficult ones, the ones that are a little bit easier to make mistakes with. So for the most part, metric conversions, we can kind of figure that out. Okay, I know that there are 100 centimeters in a meter, and so I can either slide the decimal around, or I can multiply by 100 or divide by 100. And those are usually pretty easy for us to do, as long as we remember the correct conversions. When we get into conversions like this, where we've got square units or cubic units, remember I talked about this at the very, very end of Friday, and the overall idea that we had to kind of reconcile was that when we have a unit that is squared or a unit that is cubed, there's two approaches that we can take. One of the approaches that we can take is we can recognize, okay, well, if the unit is cubed, the conversion is going to be cubed as well. And so I can cube both sides of the conversion and just plug in the cubed version of the conversion into my conversion factor here. So I could do that in this case, and with proper rounding, end up at 520 cubic centimeters. Similarly, instead of cubing the conversion, I could just simply do the conversion multiple times and end up at the same place. So if I want to convert inches into centimeters, I know that the conversion is 2.54 centimeters per inch. If I want to do cubic inches into cubic centimeters, it's the same thing. Only instead of applying the conversion once, I have to apply it for each of the three dimensions. So once for the length, once for the width, once for the height. And so when I do that, that conversion happens 1, 2, 3 times. I end up at the same answer, 520 cubic centimeters. So really how you get there is not the issue at all. The issue is making sure that you understand that the conversion itself is derived directly out of the conversion that we already know. We already know the inches to centimeters conversion. It's just a matter of how do we apply that conversion to do the calculation that we're being asked to do. So I can attack it at the conversion level, like the bottom example, or I can attack it at the dimensional analysis level and just make sure that I do the conversion the proper number of times. And if this was a square instead of a cube, I would do things twice instead of 3 times. I would square the conversion instead of cubing. So that's one kind of conversion that can be problematic, let's say, for some people. Another kind of conversion that can be somewhat problematic is when we start to look at density. Now, density, we don't usually think of, or we have not usually thought of, as a conversion. We usually think of density in terms of the density equation. Density is equal to the mass of an object divided by its volume. D is equal to M over V. And if we're calculating density of objects in a lab, that's exactly what we do, right? We find the mass of the object, we find the volume of the object, we take the ratio of those two, that gives us the density of the object. Did something similar to that earlier this week in lab, in the measurements lab. But what we have to understand is that this density equation also can be interpreted like we would dimensional analysis, as a mass divided by a volume that are equivalent to each other. This object has a mass of 33 grams and a volume of 17 milliliters. Or in ratio terms, whatever 33 divided by 17 is, 1.9 or whatever, 1.9 grams divided by 1 milliliter. Well, from that particular perspective, then, we can actually solve problems like this using dimensional analysis and using the density as a dimensional analysis factor. So the density of water, 0.99823 grams per milliliter. We can think of that as an equivalency. For water at 20 degrees Celsius, 0.99823 grams of water is equal to 1 milliliter of water. And just like we did with centimeters to inches, with kilometers to meters, with deciliters to liters, with any other conversion that we did, anything that we could set equal to each other, we can manipulate into fractions. So if I want to turn grams into milliliters, I can use dimensional analysis, where I can take this conversion and say, okay, look, I've got grams of water here in the numerator. Well, let's put the grams of water of the density in the denominator. Those will cancel out. And now I have milliliters of water that I'm working with. I can do that calculation relatively simply. Some other things to kind of draw out of our density conversations. We know that density does give us an idea of the concept of floating versus sinking if I'm comparing two objects to each other. So we usually do this in terms of water because water is kind of our most common liquid component that we would use in experimentation. And so we think of things as being relative to the density of water. Density of water, by definition, 1 gram per milliliter at 4 degrees Celsius. Pretty close to 1 gram per milliliter at other temperatures, so long as we don't get too close to the boiling point. But with that in mind, I know that if I have a substance that has a density that is less than water, it's going to float on top of the water. And classic example, that's just our that's corn oil, vegetable oil on top of water. If I have substances with a density that is greater than that of water, I know that they will sink. And so, classic demonstration here. Here you've got what looks to be 4 different liquids on top of each other with different densities. The fact of the matter is we've got this one, this is heavy corn syrup. This is a lighter corn syrup, this is water, and that is vegetable oil. And the reason they all sit on top of each other is that they don't mix particularly well with each other because of their viscosities and their densities. And in the case of the oil, its polarity as well. And so you get those layers that literally stack on top of each other in a graduated cylinder like that. And it's very density focused, density oriented. All right, let's answer a question out of our top hat bank here. If you pour dichloromethane and water into a beaker, you will see 2 layers form. And the reason for that, dichloromethane and water don't really have a whole lot of attractive forces to each other, at least not enough to actually get them to mix. The density of water is 1 gram per milliliter. The density of dichloromethane is 1.33 grams per milliliter. Which substance is going to be the top layer? All right, just a couple more seconds to get in a response. All right. Almost all of us are on the right track here. The correct answer is water. What we have to remember is density. The substances with the smaller density are going to float on the substances that have larger densities. So dichloromethane has a density that is greater than that of water. So it is going to sink, which means water is going to float. Water would be the top layer. All right, let's take a look at some other kinds of unit conversion, dimensional analysis problems that might come up along the way or might be something that you see on the quiz. So let's take a look, for example, combination units. Speed limit on Interstate 70 between Denver and Kansas City is 75 miles an hour for most of the way. How many hours will it take to travel the 604.9 miles between the cities? For the purpose of this problem, we are going to ignore changes in speed limit, ignore the idea of stopping. We're just going to assume that Iron Man is driving the distance here because anyone that's traveled 605 miles knows that's not an easy little trip. So ultimately, we are trying to turn miles into hours. And we have a speed, miles per hour, that can do that. So there are a couple of approaches that we could take. We could take the equation kind of approach. Velocity is equal to distance over time, where we could say we've got 75 miles per hour and we want to travel to 604.9 miles. We just need to solve for time. That would be one approach that we could do. The other approach would be the dimensional analysis approach. With our idea of speed here, 75 miles per hour, we know that we are talking about a distance of 75 miles being equivalent to 1 hour of our time. We could use that as a conversion factor. 604.9 miles. And we are turning miles into hours. The conversion tells us that it is 75 miles in 1 hour. Miles cancel out. 604.9 divided by 75. My calculator spits out 8.065 and a bunch of threes. How many of those digits are actually important? In this case, it is only 2. Okay, you got to think about your speedometer. Is your speedometer reading an exact speed, or is it measuring the speed based on a variety of factors? Measuring, right? And if it's measuring, remember, measurements always have uncertainty. So we have to use the output here to figure out how much uncertainty is there. We're told 75 miles an hour. Okay, we have to be, that's a guess of some degree. So we only have 2 significant figures in our speed, which means that we can only have 2 significant figures in our time. So that means we're rounding to this 0 digit. 6 is going to round that up. It's 8.1 hours. Now, if you do the equation method, you're going to have to do a little bit of algebra here. You're going to have to get this time out of the denominator. So I need to multiply each side by time, divide each side by 75 miles per hour. And so if I do that, I get time is equal to 604.9 miles divided by 75 miles an hour. The same calculation that we just did. We're going to end up with the same sig figs, same everything else. We're going to get the 8.1 hours as well. Why do I favor the dimensional analysis method over the equation method? Algebra. It is way easier to make algebra mistakes than it is to make dimensional analysis mistakes. Because in a dimensional analysis framework, you should be able to see the units canceling out to let you know that you're on the right track. Whereas if you just take this and go, okay, well, I need to divide each side by 604.9 to get the t by itself, you're going to end up with a very small number that doesn't make sense, and you're not going to necessarily know why it doesn't make sense. You're just going to know that there's no way that can possibly be right. Because what? Let's see, we're talking about, about 0.12 hours. That's a little unreasonable for a 605-mile trip. So when we deal with combination units like this, we have to be careful about them. So dimensional analysis should help us to organize them in a way that makes some sense to us. Here's another place where we can go wrong. What if I have units that need to be converted in both the numerator and the denominator? So here I have an example of fuel efficiency. I want to change my fuel efficiency from the customary units, miles per gallon, into the metric units of kilometers per liter. See this a lot with international car brands, especially. You know, if you have an imported car, it might present fuel efficiency in kilometers per liter because that's how gasoline is sold, is by the liter. And the unit distance of note there is kilometers. But if you're trying to figure out the conversion rate for yourself, you gotta do a little bit of the work there. So here I have 41.7 miles per gallon. And so again, we can think, just like we did with miles per hour, this is a unit, a ratio. 41.7 miles is equal to 1 gallon. And so when I write my starting information, that's how I'm going to put it out there. And this is what I would encourage you to do. If you're dealing with a combination unit, separate the units physically from each other. Don't just put in M miles / gallons, because it'll be very easy to lose track of whether those gallons are in the numerator or the denominator. Because you're going to write it, it's going to look like it's in the numerator when it's not. Separate the two from each other. 41.7 miles divided by 1 gallon. And since I have to turn both of those into another unit, I'm going to have to use multiple conversions to get there. So I need to turn the miles into kilometers. I need to turn the gallons into liters. I need to do both. I can't do both at the same time. I need to split them out into their own separate steps. But I do need to do both. And to help with that, I need conversions. And so the conversion table that we are looking for is not actually found in this slide deck, but it is in your book. And so if we go to your textbook, we would be able to find what it is that we're ultimately looking for here, which is a bank of values. The other thing that we can do, and I'm just gonna go ahead and do that, is we recently got access to Top Hat Ace. Top Hat Ace is Top Hat's AI platform, and we can do simple questions like that. What's the conversion between miles and kilometers? Now, ACE is somewhat experimental. So it's not as fast as like the ChatGPT or some of the other ones that are out there, but it does give us, in this case, what we're needing. The 1 mile is 1.609 kilometers. So we can use that information. And then we could do it again. So a gallon is 3.785 liters. The one thing I want you to think about, and it's really important, you know, AI as a tool can be really useful to you in a class like this. Now, each version of AI has its own specific drawbacks and benefits. But if you get stuck on something and you're not exactly sure how to proceed, asking an AI bot is completely okay to help you to try to figure out how to get unstuck. And so, you know, you're perfectly allowed to use Top Hat Ace or ChatGPT or any of those other tools to help you with this class. Ultimately, it falls on you to actually learn the information from them. So, you know, while it may be tempting to put your homework problems into one of those and have them solve it for you, ultimately that's not going to help you in the end, because in the end, you're going to need to be able to reproduce how to do the process on a quiz, on an exam, on a proficiency. And those parts of the class are way more of your grade than your homework is. So use it as a learning tool. Use it to kind of help you figure out where to go next and get stuck. But don't use it to do your tasks for you, because ultimately it's going to fall short in helping you to understand why the answer is correct. All right, so we've got our two conversions now. Let's go ahead and solve. So for the first one, I've got miles I'm turning into kilometers. So I've got miles in the numerator and kilometers, or excuse me, yes, I've got miles in the numerator here, which means it needs to be in the denominator of my conversion so that they cancel. The numbers here, 1.609 to 1. The other conversion, I need to turn gallons into liters. Now here's where I have to pay special attention. My gallons are in the denominator of my initial measurement. So thus far, pretty much every example that we've done, we've had the unit that we're trying to cancel in the numerator, and so we put that same unit in the denominator of the conversion. It's the opposite. We've got the unit that we're trying to cancel in the denominator, so we need to make sure that the unit that we're canceling it with is in the numerator so that they actually do cancel. If I don't do that step, when I go to do the conversion here at the end, if I just kind of follow the pattern I have been, in the end, I'm going to see, oh, wait, I've got gallons here and liters. So my final unit here would be kilometers times liters over gallons squared, which doesn't make any sense as far as the unit is concerned. And it's certainly not the unit that we were asked to do. So make sure that you pay some extra attention to that idea as you're doing these kinds of calculations. My gallons need to be in the numerator, my liters in the denominator so that the gallons cancel. 1 gallon is 3.785 liters. Everything has canceled other than the kilometers and the liters. So now last step, 41.7 times 1.609 divided by 3.785. This time, 3 significant figures. Our initial value was 3 sig figs. I wanted to make sure you notice that ACE gave me more digits for each of the conversions than what I put here. I could have used all of them if I wanted to. Really, I just wanted to make sure that I used enough of those digits that it didn't limit my original measure. So 3 sig figs in the end here is 17.7 kilometers per liter. That would be my fuel efficiency in metric units. So that concludes our look through the kind of those last few objects, last few kinds of conversions that might give you a little bit more trouble than most. Combination units, square and cube units, units that involve measurements. So hopefully that helped you. Hopefully that helps you get over the hump as far as finishing that assignment due tonight. But on your way out, before you head out for the weekend, make sure that you put this last question here so you get that final mark of participation for this module. And then once you have done that, you are free to go for the day. Thanks for your attention. Have a great weekend. I'll see you Monday.